Hey everybody, and welcome back to Linear Algebra Online. So I want to start and prove actually another one of those properties that we saw with orthogonal matrices that were in the last slide from the last video. And this is the one with the determinant piece. So if we're talking about these sort of isometry matrices and things that preserve distances, it makes sense that the determinant should be plus or minus 1. The minus is just there as like a directional sort of change. But, these determinants measure after a transformation the sort of scale factor change of a chunk of space, right? And it's saying that if you don't change the distances, then the determinant should stay 1, or maybe you're just changing direction kind of piece, and that would be like a -1 determinant. So to do this, all we have right now is just Q is orthogonal, okay, and we're going to prove this. So our kind of normal go-to for Q being orthogonal is that you could just say since Q is orthogonal, we know QTQ is I. And we want to get in the determinant somewhere into this problem, right? So we might as well take the determinant of both sides. So determinant of QTQ should equal determinant of I then. And then we're just basically going to use determinant properties. Determinant of a product is the determinant of each of those things in the product. That's the way I want to say it. We also know that the determinant of the identity is 1, right? And so, we now know determinant of Q transpose times determinant of Q is equal to 1. And there's another property that just says the determinant of the transpose is equal to the determinant of the irregular matrix. So really this is saying the determinant of Q, let's just say, is determinant of Q squared, I should say, is 1, right? And so then, this implies the determinant of Q is equal to plus or minus 1, which does it. So pretty much just straightforward determinant properties to do that one. I thought this was kind of an interesting fact. Don't remember if this is actually in the book or not, but it is a good thing to kind of just file away. If you have, this is true for 2x2 matrices, so if the determinant is equal to 1, then it's a rotation matrix, okay? And if the determinant is equal to -1, then it is like a reflection matrix. So both those kind of matrices are isometries and orthogonal. And so, so it's kind of a neat classification of those kind of matrices. All right, so the main goal of what I want to talk about today is something called orthogonal complements and projections. So what we're actually building to here is this thing called the Gram Schmidt process, which I'd said very briefly in one of the previous videos in this unit. And it's really the technique in which we can build a orthonormal set of, it doesn't even actually have to be normal, but an orthogonal set of basis vectors, and kind of recreate things like I hat, J hat, K hat sort of stuff, but maybe, off axis now. So there's things in material science where you want to describe some sort of lattice structure, but the lattice structure has, it would be really easily to be defined in different orthogonal basis, and so you want to do a change of basis, and in order to do that, you're going to need to know how to even create the new basis, and that's where Gram Schmidt comes in. And so there's actually some formal terminology that helps us get to Gram Schmidt, and that's kind of the plan for today. So the first thing I want to talk about is something called an orthogonal complement. So the set of all vectors that are orthogonal to some subspace W in Rn is called the orthogonal complement of W, and it has this kind of weird notation. It literally is W with like a little perpendicular symbol like that. That is like the formal way we write it. So in symbols, what I'm saying is for like some V in Rn, then V dot W equals 0 for all of the W's in this space, okay? Basically, it's like the set of all perpendicular things to something else, okay? So, if W is like a plane, let's say, we're talking about all the perpendicular, all these perpendicular vectors. It could be that one. All sorts of perpendicular vectors, right? It's the W could be this plane, and then these normal vectors are the things in W perp. And that's actually how I say it. W perp. That's how I say it. These are just some properties, and actually I'll prove some of them at some point, but a lot of them are pretty straightforward. So W perp is a subspace of Rn. The orthogonal complement to the orthogonal complement is the 0 vector. And that makes sense because, if you kind of, you look at what's perpendicular to like these normal vectors, right? You're kind of going back into the plane. The only thing that would satisfy this definition is the 0 vector, right? And then if you intersect W and W perp, you should only have the 0 vector. It's the only thing that's in both. And this one's almost practically the definition. It's basically saying if a space is spanned by W1 through WK, V is in W perp. If and only if V in here dotted with any of these things equals 0, right? That's just what it means. Like, we're just saying take this purple vector and dot it with, some vector down here in the plane, and they should be perpendicular, so you get a 0 dot product, right? So it's just a special set of vectors, okay? But it's going to play an important role in finding something in Gram Schmidt. So, and this is kind of building even more to it. You'll see this come up in a future video here. All right, so based on this picture, which I didn't want to circle, this picture, V, right, is can be defined as the sum of two things, okay? And I'm actually going to, I think for the sake of writing, so we have the projection of V onto U down here, and this right here, this thing perp of V onto U, this is basically, if we think of, I should say, U, like think of W on the last slide as just kind of being built out of the vector U, right? So W is like, here it was a plane, but now I'm saying the set space W is like just one vector. So this would be a vector in W perp, okay? And this can basically be thought of as just something like in W, right? And so I could just call this vector W perp and this vector W. And so based on this image, right, V, you can see can equal W plus W perp, right there, okay? W, that's bad W. W plus W perp, okay? And we could actually always do this with any vector, right? I'll erase this just because I don't have a ton of room on the slide, but even if you have the vector, 1, 2, right? You can think of it this way, right? You can think of 1, 2. This is like my vector V, right? And I'm saying V equals the vector 1, 0, which lives in one space, right? And then let's actually do some colors, right? So this vector, and then plus this vector which is, of course, 0, 2, right? And so I'm just saying that kind of thing where we can build a vector out of like two perpendicular basis vectors, right? I could build it here out of 1, 0 and 0, 2, both perpendicular. And if you add them together, you get V. So get rid of that. This kind of gives us like a natural way to decompose really any vector, right, into something that lives in that space W and that space W perp, okay? And this actually is a formal thing, and when we write a vector in this way, we say we have found the orthogonal decomposition of V, okay? We've basically just broken V down into two parts that are perpendicular to each other, right? And this thing can actually be extended to any number of dimensions, right? I could have put a 3D vector down here, and I could have built it out of 3 perpendicular parts. That's fine too. But you could even do something else. You could even, in a sense, always break it down into specifically 2 vectors. So if I take this, okay, I can basically decompose V into still just 2. That red one would basically be the projection of V onto the subspace W down there in the plane, right? And then I could have a vector here, right? And this one would be like the perp of V in regards to W. So it's kind of like the higher dimensional version of this, if you can see it, right? And I could say V here, right, equals, let's again call this a vector in W perp, and then let's call this thing a vector in W. So I could break down V here into a vector in W, right, and plus a vector in W perp. Yeah. So you actually could always do it with 2 vectors like that. And in higher dimensions, the thing that gets a little trickier is how do we get this vector, okay? Because if we have V and we have that, we can always get this one by just doing subtraction, right? We could always get W perp here by just doing, what would it be? V minus W, right? Because if you just have V and then you go backwards, right, you would get this one. So the question becomes, how do you get this red vector? But it's actually not too bad, because if you have these orthogonal kind of vectors to describe W, like U1 and U2 are like basis vectors for W, then you can basically do projections onto those and then do a sum of projections to get this. So what I'm saying is projection of V onto W, all right, would equal the projection of V onto P1 right here, right, plus the projection of V onto P2, right, which would go like this vector now plus this, and that would give you this red vector, right? In general, and it gets much harder to draw, right? But you could always do this. If you had, so I guess I should add here, assuming a set like U1 through U like sub K of perpendicular basis vectors. Should know how to spell that word by now. You can always just do this kind of same exact argument. You could do, the higher dimensional version of this would just be adding together more of these kind of things. And, like in 3D, it kind of would look like this, like go over in like this direction, then take a turn, go that one, and then go up or something, right? And that's how you could get the projection from a 4-dimensional space onto a 3-dimensional space, which is a little hard to think of because we're getting into 4 dimensions there. But it would basically just extend really naturally from this. We would have projection of V onto like whatever U1 is, plus projection of V onto U2, and so on, so on, so on, up to projection of V onto like U sub K, right? And that idea is how we can always get a vector that is sort of in the shadow of some other vector V in a subspace like this. And then we could take that vector, we could subtract that vector from V, right? So we do V minus this vector. Then we could always get one of these. And then we've started creating a perpendicular basis, and that's more on that to come. That's what gets into the kind of Gram Schmidt process that we'll talk about pretty soon. All right, so this whole process it can be made a lot more sense, I think, if you do an example with it. So what I'm going to do here is I have like my subspace in R3 is this plane, x minus y plus 2z equals 0. And I have a vector 3, negative 1, 2. And I want to find two things. The orthogonal projection of V onto W, which is like this vector down here, okay, that one we were just talking about in the last slide. And then I want to find the component of V orthogonal to W, okay? So let's color code this. So that one is projection of V onto W, and then this one, the component of V orthogonal to W is this thing up here, right? And for that one, right, this perp V onto W vector can just be found by V minus the projection of V onto the subspace W, right? And so really the work is finding this yellow vector, and then if we find that, this is just going to be a simple subtraction. We'll just go boom, boom, and then we'll have that vector. All right. So the first thing we got to do is we've got to find some perpendicular basis vectors for W, right, down here. We basically got to find some things in line with these axes, let's say. And they better be perpendicular, and then you can use those and just do like projections in order to get it. So the normal vector, right, to this plane is just 1, negative 1, 2, right? And so we've got to find something that is perpendicular to the normal, right? Because the normal is going to be in line with this, and we want to be in the plane for a direction vector. So, you could take like U1, which is typically what they call these things, to just be 1, 1, 0, right? 1, 1, 0 is perpendicular to that. And then, if you wanted to do like a cross product thing or something, you could do that. But you could also just like figure it out just using, because these numbers are pretty nice, right? You could have like another vector U2, which would equal, let's say, negative 1, 1, right? Because so far now it's 0, right? Negative 1 plus 1 is 0, and then this could really be anything. And I've just got to make sure it cancels out this, right? So it gives me 0 here too. So I got negative 1 times 1 is negative 1, minus 1, right? And then, so I'm minus 2, right? And if I've got a 2 there, then I would need this to be a 1. So I'm thinking about mental math, and it's hard for me. That would do it. So these vectors are perpendicular, right? And So now I have U1 and U2, and then to do the projection of V onto the subspace W, it's really just the sum of two projections. It's V onto U1 plus projection of V onto U2, right? And so if I do those out, I'm not going to probably go through all this calculation. The scalar on this first projection is like 1. You get like 2 over 2. You know how to do projections at this point. And then this one should be negative 2/5, and then you got this basis vector. And then you would get 5/3, 1/3, negative 2/3. I did my math right, I think I did. So that vector is this like projection of V onto W, right? What I really just did there was I basically went and I found this kind of vector, which was right in line with that. It doesn't look good. And then I found this vector, right? And then I just added the two, right? And it's almost like I wish I could like pick these vectors up, but I went like over and then through there, and I just made that triangle down there, which then the resultant is the it's now purple. I'm going to make it purple. So this purple vector is right here. Then to get that vector, you just literally do a subtraction. So you can just do kind of for the other part of the problem, which I've mixed colors, and that's probably really confusing. Do it in blue. Yeah, I want to do V, minus this vector 5/3, 1/3, negative 2/3. And if I do that, you would just get 4/3, negative 4/3, 8/3. And that would be it. So we have decomposed V now into, we've done the orthogonal decomposition of a vector in 3D, right? It's much easier to do this definitely in 2D, which is why I wanted to go through an example in 3D, but really just kind of keeping track of the geometry is a little confusing. And I do suggest you go through and maybe think about an actual example in 2D too, just to make sure that you fully understand it. But the process that works in 2D and 3D extends really nicely into higher dimensions, and you really can just keep doing these projections like we just did, and you would be able to then add them together, and you would get these kind of projections of a vector onto a subspace, whether it's a one-dimensional subspace like it was here, a two-dimensional one here, or 3 or 4 or 5 or whatever. And then once you have that, you can always get perpendicular things that live in W perp, which is nice. So whenever you do this, it's good to sort of do a few checks just to make sure that everything's kind of making some sense. So when finding the perpendicular component, this thing, it's a good idea to check that it's a scalar of the normal vector, right? So the normal vector in the last problem was 1, negative 1, 2. And we got the perp vector to be 4/3, negative 4/3, and 8/3, right? And so, sure enough, right, that works. You can see, 1 to negative 1, 4/3 to negative 4/3, and then double, right? So that's like the kind of stuff I do is I just double check, okay, does this fit with that, right? And it does. It's also a good idea to check that the projection of V onto the plane or space, 3D, tesseract, which is like 4D, satisfies the equation of the plane. I should really have space or tesseract. And that's also pretty easy to do, right? You can just take in the last problem, the plane equation was x minus y plus 2z equals 0. And if you go and just take our vector 5/3, 1/3, negative 2/3, so 5/3 minus 1/3 plus 2 times negative 2/3, sure enough, equals 0. So good thing to just check just to make sure that you did this stuff correct. All right, so I just want to prove like one thing that's probably fairly intuitive, but basically just that the dimension of like a subspace W and the dimension of this W perp should equal the space that they live in, right? Where W is just subspace of Rn, right? It's like if you have that plane is W that I was kind of talking about early on, and then you have like W perp right here, and you're in 3D, you have like 2 dimensions plus 1 dimension, right? And that equals 3 dimensions, which is pretty intuitive, but it's also just like good example of like proofs here. So what I'm basically going to just utilize is that really the definition of a basis. So a basis is a linearly independent set which spans the space, right? And we know that definition from a while ago, but that's really what I'm going to utilize, okay? So I'm going to start off and just say this, right? So I'm just saying that let's just have U1 through UK be an orthogonal basis for W, and V1 through VK be an orthogonal basis for W perp, right? Then what I've got right now is that the dimension of W equals K, and dimension of W perp is L. Wait, did I do that backwards? I just wanted this to be L. So those are V's too. V1, and I also kind of missed the comma, I think, a little bit. So V1 through VL, so dimension of W perp is L. U1 through UK, dimension of W is K. All right, so this is basically what I'm going to try to show. So I'm going to show that this basis B, which is U1 through UK combined with V1 through VL, is a basis for Rn, and this thing, we know it has dimension L plus K, and we know Rn has dimension N, so if we can do that, we basically show this. That's the idea. The first note, everything like Ui dotted with V sub j equals 0, since U is contained in W and V, U sub I is in W and V sub j is part of W perp, right? And so it forms an orthogonal set, and thus is linearly independent. So this is good because it does the first part of our basis for us. We just need to now show that it also spans the space. And we know it's linearly independent because that's just like a result of orthogonal sets. So, if something back in the previous video, I was saying that I think I wrote it up as like it's a property and the proof was duh. But that is basically the idea for that part. It's just since this set, each of these equals 0, then you have an orthogonal set, and orthogonal sets are linearly independent. To show the span part, I think I'm going to need more than 1 minute, so I am going to stop this video and then I'll show the span part in another video because it's a little tricky and I'm going to have to rush through it because I only have a minute left.